Exercise 10, Kernel 1. A good hint to solve this problem lies on using the Bernoulli distribution that allows for binary choices, zeros and ones, based on a certain probability p value. On cell C84, insert the following function to calculate the probability of abnormal weather conditions based on the fact that they happen 100 out of 365 days. Equals C83 divided by 365. This is the probability of an abnormal state of nature. On cell B84, insert the probability of a normal state of nature as its complement. Equals 1 minus C84. The probabilistic definition of the state of nature comes in cell C85 with the function equals risk Bernoulli open parenthesis, C84, close parenthesis. By placing your cursor on cell C85, once the distribution has been typed in, you can always view the previously created distribution. The chart for this cell looks like this. This distribution means that during a simulation with enough iterations being run, approximately 27% of the outcomes will generate a 1, whereas 73% of the iterations will generate a 0. Next, on cell C78, insert the following conditional function. If, open parenthesis, C85 equals 0, comma, risk PERT, open parenthesis, B80, comma, B81, comma, B82, close parenthesis, comma, risk PERT, open parenthesis, C80, comma, C81, comma, C82, close two parentheses. This formula will generate either one of two PERTs contingent on the probabilistic value of the Bernoulli outcome, either a 0 or a 1. In other words, in approximately 73% of the probabilistic cases hinged on the Bernoulli distribution, it will generate a PERT under normal conditions, whereas on 27% of the cases, it will generate the other PERT distribution under abnormal conditions. This cell on C78 needs to be declared an output. Therefore, click on the Add Risks Add Output button to define the cell as an output. The following suggested name will appear on the name definition window. Get rid of all the text after the slash to only leave the text name, conditional distribution with 2 states. After clicking OK here, the cell will now be declared an output and the function will look like this. Equals risk output, open parenthesis, double quotes, conditional distribution with 2 states, double quotes, close parenthesis, plus, open parenthesis, if C85 equals 0, comma, risk PERT, open parenthesis, B80, comma, B81, comma, B82, close parenthesis, comma, risk PERT, open parenthesis, C80, comma, C81, comma, C82, close two parentheses. Now run a simulation with 10,000 iterations. If you have your demo mode off, this will run very fast. However, if you run your simulation with demo mode on, you will see the updating of the simulation as much as 10,000 times on top of Excel and your chart being also updated 10,000 times. By clicking on either one of the first 3 icons of the simulation progress window, the user is able to toggle on and off the display of updating a summary window, the Excel spreadsheet model, and the output chart being updated. Leaving these options on can be very demonstrative for users who want to understand the nature of the Monte Carlo simulation process. However, this demo mode on is significantly slower than running your simulation with both options, updating Excel and updating the output chart, off. Both options can be turned on and off any number of times during the simulation run. Do notice also that the forecast calculated runtime and iterations per second calculations change under different settings for both options. On the other hand, The choice on 10,000 iterations is just a recommendation. Any number of iterations can be defined from 1 to up to 32 million. In general, the larger the number of iterations, the better the precision or convergence of the results, but also the longer time it takes the simulation to run. Achieving convergence or precision on your model becomes an ever-increasing demanding task as such convergence achievement behaves decreasingly on a non-linear fashion. The simulated output graph is shown next. Observe the extremely long tail that is generated on this synthesized integrated distribution. A single PERT by itself would never be flexible enough to generate such a long right tail. You can stop the exercise here, having generated a simulated function. However, it is always possible for at-risk to fit the 10,000 iterations and propose a fitted theoretical distribution that integrates the two PERTs being pivoted with a Bernoulli. Use the settings icon on the output window to fit the dataset. Simply click OK to proceed to fit output. A suggested gamma distribution will be the best fitted distribution according to the AIC. We now write this cell back in cell C86 equals risk gamma, open parenthesis 1.3886, comma, 24.024, comma, risk shift, open parenthesis 50.027, close two parentheses. In other words, if you were to use this distribution function for another model that synthesizes the two possible states of nature, you would not require the usage of these three used distributions. The Bernoulli plus the two PERTs. One single synthesized gamma distribution would do the job for you.